Last time our discussion was about signal fading. Fading may happen for many different reasons, may have many different periods ranging from seconds up to years, and we have also many different statistics, many different probability distributions to model this fading, to trying to guess that particular region where we have few measurements, and this particular region is when we have a dropout of our link. For us, the most important kind of fading that we're further going to talk today is multipath. Not really fading, but also other effects we get. So where is our multipath problem? Multipath is the most disturbing event in mobile communications. And the problem is usually we do not have a direct line of sight. We may be using reflections. We may be using diffraction or some obstacles. And the result is, on the receiving side, the result is signal fading. Here, the first thing is the user is probably moving. That's likely. The user is going to move at a certain velocity. But also, the obstacles themselves may be changing, and that's the reason why we get some fading. So we should write here the intensity, so electric field, just the magnitude here, and here time. We have some dependency, time dependency here. That follows some probability distribution. Last time we only talked about intensity fading. We didn't even consider any other effect on the radio signal. And this intensity fading makes sense as long as the signal bandwidth is quite small, is much smaller than maybe the fading effects. So the fading effects may be this period of fading here. This period of fading. Better writing, better plotting this fading, not as a function of time, but as a function of frequency. So at any particular instant, we are trying to plot our transfer function of our channel. So we have here the frequency omega, and here we have h of omega, and mainly we are interested in the magnitude, though we may have to correct the phase as well. And here we also have a certain frequency dependence. So now, talking about the frequency dependence, this frequency dependence has a certain period. And this period here, this delta f here, in the frequency, or delta omega, better to write it delta omega. If I have the scale plotted as omega, I have to write delta omega here. Delta omega here. So what we need to know two things. We need to know what is the actual bandwidth required by our user. And the other thing is what is now the period, say the period between two minima, two consecutive minima, in the frequency response of this channel. What are the figures here? Well, first let's discuss the urban environment to see what is going on with the frequency domain. In the urban environment, we have to talk about the difference in length, because this ray has maybe L1, this has L2. What is the approximate difference in the length of the rays going from the transmitter to the receiver inside our link? And this was measured in practice for all known systems. Let's just draw an example here. So this delta L may range between 200 meters up to perhaps 1.5 kilometers, where in which frequency range we have to also talk about frequency range about the system that's using this. This is at the frequency range of 450 megahertz. The first mobile phones were built first automatic mobile phones. I don't mean manual switching of the frequency, but automatic setting of the switching. So hand-free operation. And the first mobile phones were at 450 megahertz. The higher we go with the frequency, the shorter becomes delta L. Now, of course, this delta omega in the frequency domain, delta omega is now 2 pi times delta F if we go to standard frequency, not angular frequency. What can we tell about this delta omega or delta F here? This delta F will be approximately C0 divided, the speed of light, divided by delta L. So if I recalculate this distance into the frequency domain, this delta F will span between 200 meters is 1.5 megahertz, down to the longer the distance, the shorter the period in the frequency domain. 1.5 kilometers is now 1.5 kilometers is now around 200 kilohertz. And these are figures that are given for a certain environment, for a certain frequency range. The higher we go with the frequency, so if our system is using higher frequencies, then the consequence is that probably the range of these higher frequency devices will be shorter. And also the difference in the path length will be shorter. So delta L will go down, and delta F will go up. If we go to higher frequency, to communication systems that are using higher frequencies. So we have to keep in mind that these measurements were made right at the beginning. Say, this is almost proportional to frequency. The higher the frequency, the shorter the range of the communication system. The shorter the range, and usually it is comparable to the shrinking of the shrinking of the delta L is compared to the increase in the carrier frequency. So if I call this F0 here. So now we know one of the figures. But what is now the bandwidth of the user? We may have different users using different bandwidths, also maybe using different kind of modulation. to achieve some purposes. So everything started at 450 megahertz with analog frequency modulation. And analog frequency modulation that required a bandwidth of 15 kilohertz. Typical value was 15 kilohertz, but useful bandwidth. So such a user was a relatively narrow band user. A narrowband user will typically have its user bandwidth, if I say BU here, just to stress that it's the user, is much smaller than delta F. What does the narrowband user see in such an environment? He mainly sees, he mainly senses some amplitude change, like here. We're talking about the strength of the signal at the side of the user. He sees amplitude fading, signal fading. So here we can only talk about intensity fading. And the discussion of the previous lecture we had 1 week ago is exactly that. What is the probability distribution of signal intensity at the receiving side? Now, 15 kilohertz was a given figure for analog frequency modulation, voice, for voice transmission. Now, users do not only have just voice transmissions, users may have broader band signals. What about a broadband user, and how do I define the broadband user? A broadband user will have its user bandwidth probably larger than this delta F, here, than this fading period. What is an example? You are probably too young to talk to you about these things. Have you ever seen analog TV, analog television? Are you old enough that you have seen? Because it disappeared 15 years ago, so that's the reason why I don't know whether you still know what analog television was. So the example here is analog TV. Analog television that has a useful bandwidth of, say, 6 megahertz. I want to use here analog examples, not to going to any digital or numerical, just to avoid confusion. Because analog is very easy to define, it's very easy to understand what is going on. What is the problem with analog television? Maybe you're just too young to discuss this thing. But the problem here is multipath distortion. What was the consequence of multipath distortion? Were ghost images. So in parallel with the picture you're actually trying to watch, or the movie you're trying to watch on analog TV, you saw also a ghost image, if you had multipath distortion, a ghost image moving left or right compared to this distortion. Because one television line in analog TV was 64 microseconds long. So here we are talking about a few microseconds, say up to 5 microseconds here. So this multipath here
is comparable to the line period. So picture the ghost image actually shifted horizontally with respect to the true image. And this was a major problem in analog TV, and the countermeasure was antennas. You needed directional antennas. You may remember that for a voice, for an audio radio receiver, you just throw a piece of wire and the radio works. Well, for the television set, that doesn't work out. For the television set, if you plug a piece of wire in an analog television set, you see the main image and many ghost images mainly shifted left or right from this image. So, using directional antennas and especially a good front to back ratio. Having a good front to back ratio because this back reflection has a large delay compared to all forward rays from the transmitter to the receiver. This backward direction has the hugest amount of delay, and that means a huge amount of distortion. Also the most shifted ghost images. And that's the reason why in the years of analog television, that analog television lasted for almost 50 years, from 1950 up to 2000. So for 50 years, people were trying to install good antennas for analog TV with good front to back ratio to suppress any reflected waves to have a good picture. So the effect is different. The effect here we had intensity fading, so intensity was gone, while here we had signal, but we had the signal distorted with multipath distortion. So effects are different from a narrowband user going to a broadband user. And the bandwidth of the user should be compared with the actual fading period in frequency domain, not in time domain, but in frequency domain, which comes directly out from the multipath length difference. So that's different. And also the countermeasures were different. Maybe for intensity fading, just an automatic gain control in the receiver, in the radio receiver, audio radio receiver was enough for this purpose. Even in a radio receiver installed in a car, in a vehicle. While for multipath distortion, quite complicated solutions had to be used. Receivers had to use highly directional antennas. And that was quite a big market, selling the antennas and installing those antennas for analog TV sets. Now, all these things here, multipath distortion, also applies to anything we want to do in a broader frequency band than just the quite narrow voice transmission, analog voice transmission. And the first solutions, both for analog TV and for the first digital mobile phones, they used exactly the same solutions. The solutions were to use a filter, a correction filter inside the receiver, an adaptive filter. So if I look at my radio link now, here I have the transmitter, I have an antenna. On the receiving side, I also have an antenna. Now, this receiver, okay, has some amplification, the receiver inside. But now, what do I do with this signal? From this signal, I actually subtract some signal, some corrections. And what are going to be my corrections? My corrections are going to match what the channel is doing. So here in the channel, I have a direct ray. This is direct. I have maybe a reflection 1 from an obstacle here. I may have reflection 2.
from another obstacle here. And the third obstacle may be a reflection 3.
So I have reflections from different obstacles. So I have gamma 1 here, gamma 2 for this reflection, gamma 3 for this reflection. And I have different attenuations of this path. So I have maybe A0 for the direct ray, A0 for the direct ray, A1, A2, A3. So what do I do with my signals? How do I process my signals? How to suppress reflection from the obstacle 1. This reflection is actually delayed compared to the direct signal. So I first get the direct signal out. I multiply this by A1 over A0. And I put here a delay here, T1 minus T0, if this direct ray had the delay T0 and this was the delay T1. And I subtract this signal from the original. So first I get the direct signal, I delay the direct signal here, but I also delay the same signal over this refracted path here. If I flip the polarity of this one here, I can exactly cancel out this reflection signal here. I do the same for the other reflections. So for the other reflections, for reflection 2, I do the same kind of processing here. I have times here A2 over A0, a delay of T2 minus T0, and I also subtract this one from the sum. And I correct for the third signal. Again, I multiply it by A3 over A0. I delay this same signal by T3 minus T0. And I subtract this signal from here. So every reflection, when it comes delayed, it gets exactly subtracted from its locally generated replica, but this one is subtracted with the opposite side. Also the same here for the second reflection, also the same here for the third reflection. So this, what this device actually is an adaptive filter. For multipath cancellation. So this seems as a viable solution to remove all reflections with a suitable network here. It seems, but it's not easy to do this. First, we cannot ask the user to actually adjust these parameters here, this multiplication constant and this time delays. This has to be done automatically. So this adaptive filter actually needs some training. To adjust the coefficients of the adaptive filter. And how do we do this training automatically? Well, we can have the user turning all the commands, but that's way too difficult for a typical user. Even this is a fixed television receiver, and these reflections don't change much. What do we have to do? We have to transmit some redundancy. In the transmitter, and that redundancy, where may it come from? It may be already present in the signal. For analog television, where the sync passes. Synchronization pulses were always clearly defined in the television standard, so we could teach our receiver to adjust its filters to remove all reflections on the sync signal. We know what the sync signal is. Also, the sync signal was the most powerful signal in an analog television transmission. And such a filter could be built. It was quite close to implementation. Some companies like Philips were already thinking about making television receivers that have such filters inside, but then digital TV came out. So this was not used, but it was already developed in the labs, say of Philips and other large manufacturers, already developed such filters. Where this thing was actually used was a GSM phone. GSM phone, and with the GSM phone had in the middle of the GSM packet. Usually data packets have sync pulses at the beginning of the packet, not the GSM phone. The GSM phone had at the beginning had data, had at the end have data, and here it had a training sequence. So the training sequence was most protected from any kind of interference or packet collisions by putting the training sequence just in the middle of the packet and train the receiver filter to make this solution. With the GSM phone, it was not everything clear right at the beginning. At the beginning, the GSM phone, this is already history, so it started with a bandwidth of 6 megahertz. They started the first trials with 6 megahertz, but then technology was not there. The semiconductors were not there. The chips were not there. They had to reduce this bandwidth to 200 kilohertz. 200 kilohertz, and they had to limit the correction length of the filters to a maximum of 4 symbols. Maximum of 4 symbols. Inside, so this delay was a maximum of 4 symbols. Delay was added. 4 symbols at 271 kilobits per second is so 135 divided by 2 is around 70, slightly less than 70, 70 kilo symbols per second. Yes, that 70 kilo symbols per second is perhaps here the GSM phone may handle here a delay of, say, some 4 kilometers. The corresponding delay to 4 kilometers. That was okay for the countries where GSM was developed, and this was Germany and France. Since the GSM phone was a political decision, the politicians of Germany and France, at that time, this is now 40 years ago, decided that the future European phone will be digital and will be GSM, and will be developed in France and in Germany. Yes, they forgot something here. If you have mountains, this delay may be much larger than 4 kilometers. So this thing worked fine in the flat regions of France, and this delay worked fine in the flat regions of Germany. It didn't work in Switzerland, and doesn't work in Slovenia anyway. In Slovenia, for instance, we typically have the delays of 10 kilometers because of the mountains. So the filters that are actually standardized for GSM phones are actually too short. This is not the only problem with these adaptive filters, multipath cancellation filters. There is yet another problem. Maybe it is easier to explain this problem that this is an infinite impulse response. Or IIR filter. And infinite impulse response filters have their own problems. What is now the problem of the filter? If my multipath here has a certain transfer function, say if this is h of omega, then our filter should have just the opposite function. This g of omega should be just 1 over h of omega to correct for everything. And now there's a problem. If I also here I should just consider a frequency range, so maybe just not starting from 0 but starting from a certain frequency. If I plot h of omega, everything is okay as long as h of omega has a function that is far below, above 0. If this is h of omega. But the response of the filter should be just the opposite. So the response of the filter should be something like this. Now, if this is g of omega, what may happen here? If this thing goes to 0, this peak here may become very large. So the filter, if this thing goes actually to 0, this goes to infinity, and the filter becomes unstable. Infinite impulse response filters have always this problem that they may become unstable, especially if a training algorithm is teaching the filter to do exactly what it is receiving from the transmitter. So this was not a good solution. It is still being used in the GSM phone. It is standardized for the GSM phone, but it's not the real solution how to solve this problem. It's not a very good solution. It's also quite limited. As I told you, GSM phone, they've ended up at 200 kilohertz wide channels, while initially they were planning 6 megahertz channels, but the electronics of the filter couldn't do it. The processing power of the filter couldn't do it. So they couldn't reach actually this figure. So now the question is how to transmit actually a broadband signal like analog TV, over a channel that has multipath. According to Shannon theory, there is no problem. If I have bandwidth, if I have the signal, I have the capacity of the channel. The problem is everything gets distorted into our receiver, and that's the issue I cannot solve. And it was quite a problem to shift from this way of thinking, trying to invent new kinds of modulation, new kinds of transmissions to solve the problem of broadband transmission. So when our spectrum is actually wider than the frequency period of the fading. And there was more than one solution to solve this problem. And not all solutions were good. So we have to discuss all of them just to see what is behind, what was the evolution. We have to go the slow evolution of technology. And in fact, we started with the wrong solution. And the wrong solution was spread spectrum and code division multiplexing. What is the trick with spread spectrum? a completely different solution to the adaptive filter. So what are we trying to do with spread spectrum? With spread spectrum, we start with a user bandwidth. But we increase the spectrum width of this bandwidth by mixing it with a locally generated spreading waveform. I will call this BR. And usually this spreading waveform BR is much larger than the user bandwidth. But this one is known. It's a known spreading sequence or spreading signal. And we actually now transmit this thing. Transmitter over our link that has multipath. What we do at the receiving side, okay, we amplify, but now we try to multiply with exactly the same spreading sequence BR. And now we take this through a narrowband filter. A narrowband filter that only has the bandwidth of B user. And here we get the B user out. What is the trick right now? In order for this system to operate, we have to provide an accurate synchronization between these two broadband sources BR. So we need sync here. We need very accurate synchronization here. And what do we get out of this signal? I will try to plot the spectra right now to see what are we starting with. If this is omega, if this is f1 of omega, or at the beginning of the chain, we only have a quite narrow signal from the users. That has here 2 pi B user. Now, as we intentionally spread the spectrum, we get to f2 of omega. So f1 of omega was here. f2 of omega is here in the R. f2 of omega. We actually get a much broader signal. And now it seems that it does not make much sense here. Really what I'm talking about. It seems it does not make much sense. So here I get a much broader signal. But now the issue is what I get here in the receiver. This after the despreading with I get f3 of omega. Now I may get 2 different things. I will plot both of them here. F3 of omega. If my signal is my spreading sequence source here and here if these two sources of this broadband signal are perfectly synchronized, and they are, of course, they are known, I get exactly the original signal that only has this B user. Okay, 2 pi B user. This is 2 pi B spreading this B R. But if these two broadband sources are not synchronized, then I get an even much broader signal, twice the bandwidth of this one here. So I get a much broader signal here. This way. Much broader signal. So this is twice 2p BR. And this one is synchronized. Where is the trick now? Our direct signal here is synchronized. But the reflected signal is not synchronized. Because it's additionally delayed reflection. Is not synchronized, so this is actually the reflected signal. So direct, reflected. And if I go now through a narrow filter here, this narrow filter, this B user, will actually filter out our desired signal, and we are also left with a small amount of interference, but this interference is very small because it is spread across a wide spectrum. So just a small amount of interference makes it through this filter here. So I can improve the signal to interference ratio a lot. My improvement is comparable to the ratio of these two bandwidths here. So I always choose to have this spreading bandwidth BR much larger than B user in order to have a large signal to interference ratio. That's the trick of SPED spectrum. SPED spectrum also allows us something different to do it. If I have another transmitter transmitting some other information like B user 1 going to another similar transmitter, but having here a BR1 that's not equal to BR that's being transmitted. This one here only causes interference because this is not synchronized. Not synchronized because it's a different, maybe different spreading sequence. It only causes interference, and also the interference spreads out to a much broader signal. So these things actually allows me code division multiple access, CDMA. It is not very efficient. Code division multiple access is not very efficient because I'm always left with some signals here in the useful frequency band. But this can be made arbitrarily low by choosing a large spreading sequence. So this can be solved. It is not, though, that good at this. So we had CDMA used in the past. It was used in the UMTS phone system. It could handle broadband signals. It could handle reflections. And in fact, every receiver was not just equipped with one processing chain. Each receiver had many processing chains, so each reflection could actually be used and delayed and corrected to make sum here of all useful signals. These were called fingers inside the receiver. There were many such circuits for every reflected wave one. So CDMA could be perhaps compete with other systems, but it was not a good idea to start with. It was also very difficult. CDMA was also very difficult to handle, because if I had code division multiple access, then I should carefully monitor the powers of the transmitters. All transmitters should come at the same power at the receiver, because if the interferer was much stronger than the useful transmitter, then we gained nothing here. We had to have all transmitters at the same power. And so power adjustments in UMTS and other code division multiple access systems was very critical, and quite a large number of the channel capacity was used just to control the power of the transmitter, to having all the transmitters tuned to the same, adjusted for the same power at the receiving antenna. So it was not that difficult to build UMTS, and it was not very efficient UMTS. This is just to go through the complete explanation what was being used in past. So the signal to noise ratio here is going to be rather poor. Yes, we can do mechanical communication, but the signal to noise ratio is poor. Signal to noise ratio. That means that the spectral efficiency, so capacity over bandwidth used, will be probably in the range of 1 bit per second per hertz. That cancels out. So the spectral efficiency of CDMA is not particularly good for this reason. But talking about 20 years ago, or now it's already 30 years ago. 30 years ago, it was the only solution to transmit broadband data over a channel with multipath. And that was the reason why it was adopted by mobile phones. Everyone knew it was not a good solution, and sooner or later it was known that UMTS and CDMA are going to disappear, and we are going to use better systems for communication in a multipath environment. CDMA was not a particularly good solution. A partial problem was also that this CDMA equipment, like UMTS, was not compatible with the internet protocols. But that's just, it was probably commercially it was very important. It was not compatible with internet. But from the theoretical point of view, you could also run internet over UMTS. You could run it, things could work, but the system itself was not efficient to start with. To start with the system, we didn't have quite a good signal to noise ratio in such a system. Using intentional spreading of the signal spectrum, and then precise synchronization of the transmitter, of the receiver. So this was not I have to mention here it in my lectures just to show you what the development was. So in the 21st century, we are getting to different systems, and I will try to talk about them next hour. Okay, so that's for this hour.